Hello Bobcats. In this video we will be discussing constant pressure calorimetry. Now this is slightly different than the last video where we talked about the calorimetry used to measure the transfer of energy from a hot substance to a cool substance, such as the metal transferring its energy, a hot metal transferring its energy to cold water, and the change in temperature. That is two substances of different temperatures. This calorimetry, constant pressure calorimetry, is usually used for measuring the energy involved in reactions, or we can say enthalpy. So let's define calorimetry one more time. So calorimetry is an experimental technique used to measure the amount of heat transferred to and from a system. Measure the amount of heat, and that's Q, measured, transferred, sorry, amount of heat transferred to and from a system. Okay. Now, most classrooms use what's called a coffee cup calorimeter or styrofoam calorimeter. So most classrooms use a styrofoam cup calorimeter. To measure this heat transferred by reactions. Heat transferred by reactions in aqueous solutions. So remember, aqueous solutions contain the compounds dissolved in water. So really we're looking at heat transferred from reactions to the water, which is the surroundings. Now, so what does a coffee cup calorimeter kind of consist of? We have or styrofoam cup calorimeter. I'm going to do the best I can to draw it. So you take styrofoam cups, usually two of them, and put them into each other, but I'm just going to draw one. So I have a styrofoam cup, and the reason we're using styrofoam cups is because it's the simplest way to create an insulated system, or as much as we can possibly get of an insulated system, in which the energy and the matter cannot go back and forth from surroundings and system, or leave a certain amount of system. In other words, I want to keep all the energy inside this cup, and all the energy being either absorbed or released by the reactants into our surroundings, and we want the surroundings to be the solution. So we don't want energy getting outside. Now, coffee cups are not the best thing, because there is some error here, but it is as good as we can get without spending a whole lot of money. And then you have a thermometer, because you have to measure the change in temperature of the water in the solution. And I'm just going to say solution from now on. So we got a thermometer in here. There's my thermometer, and I'm going to go ahead and label it thermometer, thermometer. We also have this insulation to keep as much energy in as we possibly can, so that it's all being absorbed by the water, and none of it is being absorbed by the rest of the surroundings, like the air, the cup itself, and so forth. And we use styrofoam for that. And then inside you have the aqueous solution. Now remember, when I say aqueous solution, that is containing, that's reactants dissolved in water. So I'll write that down. Reactants dissolved in water. So really, it's the water. We want the water to be the surroundings. So from now on, I'm just going to call it a solution, but really the reactants are the system, and water is the surrounding. Now, the important thing here is that this cup calorimetry is carried out at atmospheric pressure. Atmospheric pressure, because it's not completely isolated. The pressure outside equals the pressure inside. So inside the cup is the same pressure as the outside, which is atmospheric pressure. So because it's done at atmospheric pressure, that means that it is constant. So atmospheric pressure is constant. So it's constant pressure. That's why we call it constant pressure calorimetry. And because it's at constant pressure, therefore, we can say that the delta H of the reaction is equal to Q, or the heat transfer, remember, at constant pressure. Okay, so that was an important concept that we learned last time about energy, is that the enthalpy of a reaction is really just the heat transferred at constant pressure. Now, for this to help out really understand what's going on, because it's the water that's changing temperature in the solution, we're going to say that the heat exchange, or energy, Q, of the solution is equal to the mass of the water of that solution times the specific heat of water of that solution times the change in temperature of the water after the reaction. Okay, so we're really measuring the change in temperature of the water. The water is the surrounding. Now, so if the water is the surrounding, we can also say that the Q of the solution is equal to a negative Q of the reaction. So as the solution gains, it's because the reaction is losing, or vice versa, but it's opposite and equal to what's happening with the reaction. The reaction is the system. We're looking at the solution as the surroundings. Now remember, up here, because the delta H reaction is also equal to Q, we can say that we'll say here that the delta H of the reaction is equal to the Q of the reaction, because it's at constant pressure. And so again, if this is Q of the solution is MC delta T, we can say that here we can say that the delta H of the reaction is equal to, because remember we said it's a Q here, the delta H of the reaction is a negative MC delta T. Okay, and really it's the MC delta T of the solution. So when we measure this heat exchange of the solution, we're getting the enthalpy change of the reaction, or the heat exchange of the reaction. So to make sure we understand this, we are really measuring the energy that's being absorbed by the solution, or given off by the solution. But we also know that the energy absorbed by the solution is also equal to the energy released by the reaction, which is the system. And if the energy of the reaction is also known as the delta H, or enthalpy of the reaction, because it's at constant pressure, we can say that the delta H of this reaction is a negative MC delta T of the solution. And this is what we really need to know. So when we're looking at the calorimetry of constant pressure, we're really trying to find the delta H of a reaction. Now, so let's look at let's make a couple other statements before we look at a problem. So another statement we want to look at is that, to make sure we understand it, the system is the reactant and products of the reaction, and products of the reaction, and the surroundings that we were really measuring or looking at include the calorimeter, the thermometer, and the water in the solution. Include the calorimeter, which we are hoping does not absorb much of the energy because it's styrofoam. The thermometer, which absorbs just a tiny bit, just enough to get a reading. But most of the energy absorbed from the reaction is from the surroundings of the water in the solution. Okay, but it's the water that we're really hoping gets all absorbs the energy or releases energy. So we can say that when the temperature of the solution increases, which really we're looking at the water, but I'm just going to write solution now. When this temperature of the solution increases, it is because energy is being released by the reaction, which is the system, into the surroundings, or released by the reaction into the surroundings, or into the solution. which I'm going to say here is water, just to make sure. Okay. Now, because the water is absorbing the energy, it is going to increase in temperature, and it is the reaction that releases the energy, released by the reaction, so we call this an exothermic reaction. And you should get a negative delta H. And when the temperature of the solution decreases, it is due to the reaction absorbing energy from the surroundings. Reaction, which is the system absorbing energy not a Q, energy, sorry, from the surroundings. Which is really the solution or the water of the solution. And because the water is actually losing its energy to the reaction, the water decreases in temperature, and we call this an exothermic reaction. No, not exothermic, sorry, endothermic. I think I'm getting tired. Endothermic reaction, and you have a positive delta H. Okay, so let me say that again because I kind of messed up. When the temperature of the solution decreases, it is due to the fact that the reaction, which is the system, is absorbing energy from the surroundings, which is the solution, really mostly water, and the water then goes down in temperature because it's losing energy. And we say that the reaction itself is endothermic because it is absorbing energy. So in this case, we're looking at the reaction absorbing the energy. Okay. Now, let's do a practice problem. And I'm going to write the equation one more time so that you guys really have it down. What we really look at in this case is that the delta H of a reaction, or the enthalpy change or energy of the reaction, is equal to a negative mc delta T of the solution. Okay? And that's the equation we really want to look at. Now, let's do a practice problem. Let me pull it out. Where did I put it? All right. Thought I had it right here, available. Here we go. So, this is the problem from the PowerPoint. And so let's go through it. We've got 25 mils of a strong acid reacting with 25 is added to 25 mils of strong base into the coffee cup. When they're added to each other, they have a reaction. It's called a neutralization reaction. They produce water and a salt. Now, the solution temperature rises. It goes from 20.5 to 25 degrees. So because the water is rising in temperature, or the solution I should say, we know that this has to be an exothermic reaction. In other words, reaction is releasing energy to the solution, and the solution gains temperature. Because the solution is mainly water, we're going to say that it has the same specific heat as water, and because it's mainly water, we're going to say that it has the same density as water. Okay, so now what we want to do is we want to calculate the enthalpy change of the reaction. So here we're going to calculate the delta H of the reaction. And in here, in B, assuming that the strong acid has a concentration of 1.5 molar, calculate the enthalpy change per mole. So we really want to know how many kilojoules per mole. Okay? So that's what we're looking for in this problem. Okay, enthalpy change per mole of the acid. We're looking at the acid. Okay. So when I do this, part A, let's work through part A. A couple of things. We know that the equation is delta H of the reaction is equal to a negative MC delta T of the solution. So I had to find the mass. Now in this case, mass of the reaction is equal to, well, we have 25 mils plus 25 mils, so that's a total of 50 mils. But because it's mostly water, we're going to say it's 1 gram per mil. So if we have 50 mils, we have 50 grams. So I'll write it here as 25 grams plus 25 grams of the water. So we actually have 50 grams of solution right here. Okay, now it's mass. My C, or specific heat, is 4.184 joules per gram degree Celsius. And then my change in temperature of the solution, which is mainly water, is going to be final minus initial. So that's 25.0 minus 20.5. So we get a positive 4.5 degrees Celsius change. And so that's the other one we're looking for. So I'm just going to substitute up here, and we're going to say a negative 50 grams times the specific heat of 4.184 joules per gram degree Celsius times that change in temperature, which is 4.5 degrees Celsius. That's my enthalpy of the reaction, or the heat involved in the reaction. And that will equal, let's make sure all our units cancel. Grams cancels here, Celsius cancels there, so we're left with joules. So my enthalpy change of the reaction, or heat exchange of the reaction, is equal to a negative 940. The calculator says 41.4, but we only want, there's 3 sig figs, so 941 joules of energy. And of course we know that it's exothermic because of its negative exothermic, because it's negative. And it makes sense that it's exothermic because the water is increasing in temperature, because the water is gaining the energy from the reaction. So that's the energy involved in what specifically we have up here, the 25 mils and 25 mils. But for B, we want to find out how much energy per mole. Okay, so I'm looking for kilojoules per mole, and we know that we have a negative 941 joules. So I'm just going to convert that to kilojoules real quick. So that's 1,000 joules in 1 kilojoule. And then we have to have the moles. So how do I get my moles? Now, well, let's go ahead and write this out and say this is going to be a negative 0.941 kilojoules of energy, and then I need to figure out my moles. Now remember, we had 25 mils, so that's 0.025 liters, and the concentration was 1.5 molar, so that's 1.5 moles per liter. So that gives me moles, so that comes out to be 0.0375 moles. So again, if I just want kilojoules per mole, I'm just going to take this and divide it by that. So let me start here again one more time. Kilojoules per mole is equal to 0.941 kilojoules over 0.0375 moles, and that comes out to be a negative 25 kilojoules per mole. So I just want to make sure I got kilojoules per mole. And that's how we work that problem. Our next video is going to be on stoichiometry of thermochemical reactions, and I'll see you then.